Welcome to the Explainer. Today we are looking at an absolutely revolutionary leap in how we build artificial intelligence. We're talking about a completely new way to train self-improving AI systems, moving them away from static, boring benchmarks and into a dynamic, co-evolving ecosystem. Look, if you've ever wondered how we can keep pushing the boundaries of machine learning without just hitting a plateau, well, you are in exactly the right place. So, to really understand the problem we're solving today, picture a student preparing for a massive exam. If you give that student the exact same practice test over and over again, they aren't necessarily getting smarter, right? Eventually, they just memorize the answers. They learn the quirks of the test rather than actually mastering the subject. Well, believe it or not, this is exactly what happens with state-of-the-art AI right now. We train these brilliant systems against fixed benchmarks, and eventually, they just figure out how to ace that specific test without really improving their underlying capabilities. So the big question becomes, how do you train an AI when the test itself needs to continuously get harder? Okay, let's dive into this. The current paradigm is what we call static AI. This is the standard approach where an AI optimizes against a stationary evaluation criterion, like a fixed dataset or a static benchmark. The major flaw here? Stagnation. As the AI gets better, the static benchmark saturates and becomes totally vulnerable to what we call reward hacking. Basically, the AI finds clever loopholes to score high without doing the actual work. But the future? The future is co-evolving AI. This is a system where the AI adapts to a continuously moving target. Instead of a fixed test, the evaluation criteria evolve right alongside the AI itself. To really grasp how this works, we actually need to look away from computer science for a second and look at biological evolution. The framework we are exploring today is named after the Red Queen hypothesis. This is an evolutionary concept proposed by Lee Van Vallen, and it's inspired by that famous quote from Alice in Wonderland, where the Red Queen tells Alice, "It takes all the running you can do to keep in the same place." In nature, species don't evolve in a vacuum. A fox gets faster, so the rabbit has to get faster just to survive. They co-evolve. They constantly push each other to adapt. And that brings us to the core thesis of a groundbreaking new paper from researchers at the University of Cambridge, NVIDIA, and INRIA. They realized something crucial. Species do not optimize against a static environment, but adapt as their environments change with them. Current recursive self-improvement in AI was completely ignoring this central feature of evolution. To fix this, they introduced a framework called the Red Queen Godel machine, or RQGM for short, to bring this undeniable biological truth directly into the AI improvement loop. So, what does this actually look like under the hood? Well, they use a tree search over a multi-agent workspace. Instead of a single AI trying to solve a problem all by itself, the Red Queen Godel machine pairs an AI agent, think of this as the student, with an AI evaluator, which acts as the teacher. They literally share a workspace. And as the search process runs, it's not just the agent trying to generate better solutions. The evaluator is also learning how to become a better, stricter judge. They are locked in a cycle, effectively leveling up together. But wait, if the test is always changing, how do you mathematically guarantee that the AI is actually improving and not just, chasing a random moving target? The researchers solved this with a brilliant mechanism called controlled utility evolution. It runs in 4 simple steps. First, you freeze the evaluator. So for a set period, called an epoch, the rules stay exactly the same. Second, the agent recursively tries to beat that specific evaluator, which ensures stable learning. Third, when the epoch ends, the evaluator is upgraded to a stricter version based on ground truth data. And fourth, and this is key, the system performs selective erasure, wiping out the outdated scores tied to the old, easier test. The rules stay the same for one round, but the test gets harder the second the round ends. Let's move to the real-world payoff of this framework, starting with software engineering and coding tests. And this brilliantly illustrates why this coevolution is so incredibly powerful. When comparing the RQGM to a previous state-of-the-art baseline called HGMH, you can clearly see the power of coevolution at play. By introducing a co-evolved code reviewer, an AI that actively judges code quality rather than just running multi-turn code executions, the system generates a much cheaper, complementary evaluation signal. Because the AI roles share the same foundational infrastructure, improving the reviewer actually helps improve the coder at the exact same time. So what is the actual efficiency gain here? Look at this number, 1.72x. The RQGM coder achieved a massive 71.7% held-out pass rate on the polyglot benchmark, and it did so using up to 1.72 times fewer search tokens than the previous baseline. By simply letting the AI teacher and AI student evolve together, the search process becomes wildly more efficient, saving absolutely massive amounts of compute. Now, this framework also solves a huge kind of hidden problem in the AI industry: self-preference bias. To test the system beyond just coding, the researchers looked at scientific paper writing and reviewing. When you use standard large language models to grade text, they have this baked-in bias. They absolutely love text written by other AIs. They find it plausible, structured, perfectly familiar. As a result, standard AI reviewers grade AI-written papers way too leniently compared to human-written papers. To put a hard number on that bias, the strongest baseline reviewer in the study was over-accepting AI-generated text at up to 1.91 times the rate of human papers, literally almost double. Think about it. If your AI judge is handing out easy A's just because the text sounds like an AI wrote it, your AI writer is never going to actually improve. It's just going to reward hack the easy judge. This was a major flaw that the Red Queen godel machine was uniquely positioned to fix. And here is exactly how they fixed it. Because the RQGM upgrades its evaluator at the end of every epoch, the researchers introduced an adversarial pool. They took the AI papers that the old, lenient judge accepted, and in the next epoch, they actively rewarded the new judge for rejecting them. This completely forced the evaluator to become equally stringent on AI and human work. And the results? They speak for themselves. When scored by a diverse panel of judges, the standard baseline writer had an acceptance rate of just 21.8%. But the co-evolved RQGM writer, it hit 40.5%. By forcing the writer to survive a massively stricter, unbiased reviewer, the writer's quality effectively doubled. So the absolutely crucial point here is understanding exactly how a stricter test changes the AI's internal landscape. This brings us to the curriculum effect. If we look at the Spearman rank correlations, when the evaluator is upgraded and the old easy scores are erased, it doesn't just lower everyone's grade. It permanently changes which AI solutions are considered the best. You can see the correlation drop and stay low after a replacement. The new, stricter criterion completely re-ranks the archive of solutions, pushing the search into totally new, higher quality directions that the old judge would have just ignored. But you might be wondering, wait, if we constantly erase scores and re-rank everything, doesn't the AI lose its progress? Well, check out the resilient crimson line tracing through the gray nodes in the archive graph. This is what's called the backbone lineage. Even as the evaluators get harder and weaker solutions get churned right out of the top rankings, this core winning lineage survives the erasure. It proves that the AI population is truly progressing forward through the new epochs, building on its best traits instead of starting from scratch every single time the rules change. Now, to prove the absolute versatility of this framework, the researchers didn't just stop at coding and paper writing. They shifted to Olympiad-level mathematical proofs. This is highly rigid, strictly logical work. There is zero room for subjective self-preference bias here. I mean, a proof is either logically sound or it isn't, period. The researchers compared standard, static Olympiad proof graders against a co-evolving RQGM grader. And guess what? Even on these strictly objective tasks, the co-evolving approach vastly outperforms standard AI systems. And the efficiency gain here is just staggering. The co-evolved math grader reached the highest ground truth accuracy at a massive 3 times lower search cost than the fixed baseline. 3 times. Because the grader was continuously co-evolving, it provided evaluations that guided the mathematical prover toward better solutions far, far faster than a frozen static evaluator ever could. So, looking at the big picture, what are the real key takeaways from this explainer? Why does the Red Queen godel machine matter so much for our future? First, it completely overcomes static test memorization and reward hacking. Second, by sharing infrastructure between agents and evaluators, it creates cheaper, highly efficient surrogate objectives. Third, through epoch boundaries and adversarial pools, it can automatically fix deep-rooted issues like self-preference bias. And finally, it enables AI to train and recursively self-improve in open-ended domains where absolute ground truth benchmarks don't even exist yet. The researchers at Cambridge, NVIDIA, and INRIA have proven that removing static benchmarks and letting AI systems evolve against each other is the definitive future of machine learning. Which leaves us with a fascinating and honestly perhaps slightly intimidating final thought to ponder as we wrap up today. If artificial intelligence can now automatically build, refine, and enforce its own increasingly difficult tests without any human intervention, what is the limit to what it can ultimately learn? Thanks so much for joining me on this explainer, and keep questioning the benchmarks.